So in previous lectures, we talked about how polymers could degrade, but today we're going to talk about how metals can degrade. And the first idea for metals degrading is by corrosion, which we could think of as degradation of metals. So if we're thinking of degradation of metals, the mechanism by which most metals degrade is they start off as some solid form of the metal, and then they're dissolved in biological fluids. So we can think of corrosion in the context of metallic biomaterials as dissolving metals in a biofluid. And in order to have that solvation take place, we need basically two things to happen. One is it needs to be energetically favorable. Right? And if we anthropomorphize the metals, we'd like to think of those atoms of metal, they would rather be ions dissolved in solution than as solid parts of the metallic material that we've implanted. So in order for that degradation to take place, the first thing that needs to happen is it needs to be energetically favorable. And then the second thing that needs to occur is the biofluid needs access to the metallic surface. Right, so if the metal never actually touches the biofluid, then corrosion can't take place. So we'll be thinking about these two things, and as engineers, we can exploit both of these things if we want to limit the amount of corrosion that takes place. So let's think now about the energetics of corrosion. So it takes energy to strip electrons from atoms. Right? These electrons are perfectly happy to hang around the positively charged nucleus, but if we dump some energy into the system, we can basically pull those electrons off. So we can think of some metal, M, this might be just kind of any metallic atom. We could think of this as a reaction by which a metal becomes an ion with some number of charges little n, or some ion that is a positive charge of little n, and n number of electrons pulled off. So we can think of, if there are n electrons, pulled off, then by conservation of charge, the same n is the charge that is a positive charge that the metal ion would take place. But in order to pull these electrons off, we need something on the left-hand side, and this would be some energy. So we can think of some energy plus some metal atoms becoming metal ions and the stripped off electrons associated with it. So if we think back to high school chemistry, we might say, oh, we've dealt with energetics and reactions before, and a lot of times we take the energy and put it on the right-hand side of the equation. So and we think of that in terms of like a change in enthalpy or something like that. So we've seen energy on the right-hand side before expressed as a change in enthalpy, something like that. And oftentimes the units of this change, of this delta H, this change in enthalpy, would be something in like joules per mole. All right, so however many moles of reaction have happened, then there would be a change in enthalpy of our system associated with that, given by delta H. In contrast, it's a slightly different story when we're talking about electrochemistry. So for electrochemistry, we could certainly talk about things in terms of enthalpies, but there are two key features of electrochemistry that make our bookkeeping easier if we keep track of this energy in a different way. So we will think about one key feature is there are rarely these electron producing reactions happening in isolation. So first thing is there are rarely, this rarely happens in isolation. We rarely have electrons just hanging out doing nothing, right? These electrons would, if we think about them as choosing something, they would choose to hang out on some other atom or some other ion or something like that. They're not just going to hang out as electrons for long by themselves. So if there are rarely electron producing or electron consuming reactions happening in isolation, they're usually paired with the sort of opposite thing happening. So they're usually paired with, so if there's an electron producing reaction, it's usually paired with an electron consuming reaction such that there are no net electrons. So now let's think about the second key feature of electrochemistry. So we'll think about the second key feature. And the second key feature is that rather than expressing things in terms of enthalpies in joules per mole, usually electrochemists are doing things by measuring currents or measuring charges. So rather than talking about moles of things producing, I mean, certainly we could keep track of moles. Oftentimes electrochemists talk about things in terms of currents and charges. So currents would be they would measure in amps, and charges they would measure in coulombs. So now, question headed your way. If instead of talking about energy per unit mole, like we did for changes in enthalpy, if instead we do energy per charge, that would have units of joules per coulomb. So my question is, what is a more familiar unit for joules per coulomb? Well, the answer is a volt. So oftentimes when we're talking about the these reactions happening, we talk about them not in terms of changes in enthalpy for moles of reaction happening, but we talk about them in volts, and it's not the absolute energy of pulling these electrons off, but it's a relative change in energy per charge as compared to hydrogen being split into two H plus ions and two electrons. So rather than expressing things in terms of joules per mole of reaction, instead we say, all right, compared to this reaction, how much energy per amount of charge is there? So with this in mind, let's take a step back and consider a metal becoming an ion with electrons now. So we have this metal, and this metal becomes an ion with some positive charge, and an equal number of electrons are producing. And depending on how much energy per unit charge it takes to pull these electrons off, the more energy it takes, the less favorable this reaction is likely to be. Or if the less energy it takes, the more likely this reaction is to occur. So if more energy per charge is required, then this is less favorable. And if we think about this in the context of biomaterials, if usually we don't want our metal implants to degrade because these metal ions can be toxic, or it's just, leaving less of the material there, and maybe that material was structural, like a hip implant or something like that. So usually we don't want this reaction to happen, and because we don't want this reaction to happen, we might want to choose metals where this reaction is energetically unfavorable. All right, so we want to choose cases where this reaction is unfavorable. Now, we might be asking, all right, I before, just a moment ago, was talking about how this reaction almost never happens in isolation. It's always paired. So the logical conclusion, or the logical question to ask might be, where do the electrons go, right? What counter reaction is this paired with? And it turns out that there are actually a small handful of reactions that can happen in biofluids, kind of using a vague biofluids term, but there are three common cases. So there are three common cases. The first is just some hydrogen ions in solution gobbling up those electrons and becoming hydrogen gas. So we might have some hydrogen ions, right? This would be a case where maybe we have some sort of acidic solution, and there are some of these electrons that were left over or that were produced by this metal becoming an ion. So these would be electrons that were the products of that first reaction happening, and those can combine to form hydrogen gas, and then this hydrogen gas can just kind of make its way out of the body. There might be another case where we have some oxygen around, and this oxygen can combine with a bunch of hydrogen ions and a bunch of electrons, and those all can combine together to form H2O. So this is the case where maybe we have some oxygen dissolved in our biofluid, right? This happens all the time because cells need oxygen to survive. So cells can find some dissolved oxygen, the electrons find some dissolved oxygen and some nearby hydronium ions, and they all combine, and they form just more water in solution. Another possibility is if you have some dissolved oxygen and some water and some electrons produced from the ionization of the metal, then all of these can combine together to form some hydroxide. So which of these reactions happen? They're probably all happening simultaneously, but the precise type of reaction that happens might depend on pH. So which reaction is most common? Depends on pH and the concentration of O2. But the idea is that all of this stuff is constantly being replenished in biological fluids. And if all of, well, I guess, the O2, the H2O, the H+, if all of these are constantly being replenished, and all of these are constantly being taken away, then there's always a sink available for these electrons. And if there's always a sink, there's always a sink available for these electrons produced from the ionization of the metal. And if there's always a sink for these electrons, then this reaction is going to keep happening until all of your solid metal has corroded away. So you might be thinking, oh no, this is a disaster, right? I put some metal inside someone and eventually it's all going to be gone. So how do we prevent this from happening? So how do we prevent it from happening? Two choices. Choice number one is make the metal going to make this reaction unfavorable. And the other choice is we can prevent contact between the metal and between the metal and the biofluid. So let's talk about this first strategy first, and then we'll talk about the second strategy as a follow-up. All right, so now we're going to talk about cases where this first reaction would be unfavorable. So in order to do that, let's kind of tabulate lots of values. So when we were talking about how electrochemists characterize the energetics of that relationship, they do so by talking about the joules per coulomb, or the voltage, or in a sense the electrochemical potential associated with with the ionization of the metal. So, so let's quantify the energetics. So if we want to quantify the energetics, a lot of times we talk about what would be the that sort of change in energy per charge, right? So let's just talk about what some common values are for particular metals. And I'll sort them by what this potential is. Or this energy per charge. So this would be in units of volts, and the metal would be right here. So let's talk about a bunch of metals. We have gold, we have platinum, we could have mercury, we could have silver, we could have hydrogen. I know, strictly speaking, hydrogen isn't a metal, but let's just have it there for reference. We could have iron, and we could have zinc. Oh, nope. First, let's chromium before zinc. Chromium, zinc, aluminum, titanium, and sodium. All right, so we have a whole bunch of metals here that you might have seen before, sometimes in the context of biomaterials, sometimes in other contexts. And let's put down the potentials here. So gold is a positive 1.43 volts. So that means that it takes more energy to pull the electrons off of gold than it does to pull the electrons off of hydrogen. So this means gold holds its electrons more tightly than hydrogen does. And this leads to gold being a material that doesn't corrode particularly easily, right? You may have, this is why gold jewelry looks beautiful, thousands of years later when they dig it out of, tombs and pyramids and things like that. Platinum, 1.2, mercury, 0.8, silver, 0.79. So all of these are things that hold onto their electrons more tightly than hydrogen, and they're things that we might have experienced don't really corrode particularly quickly, right? We also might have noticed that gold tends to corrode, like silver in some cases can corrode, but gold is much more harder to corrode, and that's associated with gold being higher up in terms of this potential. Hydrogen, by definition, is 0. Because all of these joules per coulomb or volts are not the energies not strictly speaking, the energies to pull the electrons off of these metals, but the difference between the energies to pull the electrons off of this metal as compared to pulling the electrons off of hydrogen. So if hydrogen is the thing you're talking about pulling off of, it's going to be 0 because it's the same as what it's in reference to. And then there are some metals that bind their electrons or that hold on to their electrons less tightly than hydrogen, and those might be all of these things below here. So 0.44, chromium minus 0.73. Zinc is minus 0.76. Aluminum is minus 1.33. Titanium is minus 1.63. And sodium is minus 2.71. So what's a kind of general trend that we can pull from this? If we go in this direction, it's easier. It's easier to pull off electrons than for H2. So our conclusion might be these maybe corrode quickly. And that would definitely be the case for something like zinc, or maybe even something like iron, and definitely something like sodium, right? If you put a block of sodium in a bit of water, well, no, never mind. I don't recommend you do it, but I do recommend you look up YouTube videos of other, perhaps more foolish people doing it. It's a rather violent reaction. So in these cases, there might be a lot of metals down here that corrode quickly. Whereas metals up here, it's harder. It's harder to pull those electrons, so we'd conclude that they corrode slowly. Or maybe even not at all. And we might have seen that, but we're starting to see, hey, maybe there are exceptions. So from our experience, we might know that some of these seem to resist corrosion well. Which materials seem to resist corrosion well? Well, definitely gold and platinum. Mercury, we've certainly noticed. Mercury is actually used in dental fillings. We might have noticed that silver, if you have silver plated things or, things like that, silver can definitely resist corrosion well, particularly when it's combined with mercury. That's what people used to make old school dental fillings. But there are also a handful of metals down here that seem to resist corrosion well. For example, chromium can, and aluminum, and titanium can. So what's the conclusion? Well, these ones would definitely be explained by this thing going on here. But these other guys down here, the electrochemical potential is not the whole story. So if electrochemical potential is not the whole story, what is the whole story? Well, stay tuned for part 2. So there's these metals up here that aren't really corroding or aren't really oxidizing at all. But then there are these other metals down here that seem to resist corrosion, according to our sort of observations, our experiences, right? Aluminum doesn't really rust. But it can't really be due to its resistance to kicking off electrons. So my question is, do low potential metals such as titanium and chromium oxidize at all? Right, like if we don't notice very much rust, very much corrosion, is it that they're not oxidizing at all, or is it something else? So ponder that for a moment. And the answer is yes, they still oxidize, but the key thing is only at their surface. And a key thing is not only do they only oxidize, not only do certain metals like titanium and chromium oxidize only at their surface, is this surface oxide layer. The surface oxide layer prevents further corrosion of everything underneath. It acts as a protection. So the surface oxide layer protects. Protects the unoxidized metal underneath. Now, there didn't seem to be too much of a trend, right? Chromium exhibits this protective surface layer behavior, but zinc doesn't, but aluminum and titanium do, but sodium doesn't. So, that's not very satisfying from an engineering perspective, right? As engineers, we want to be able to model these things, predict these things. We want to come up with rules about what sorts of things will exhibit protective oxide layers and which ones won't. So what is the mechanism, right? What is the mechanism by which some metals have protective oxide layers and others don't? So in order to explore that, let's make a chart. And let's look at 3 cases. So when we look at these 3 cases, we'll sketch the surface of the metal. In these 3 cases, and the metal is basically what's going on down here. And we know that a lot of times metal kind of has a sort of, maybe an underlying regularity to it, right? The atoms all arrange in some kind of crystal structure. So here I'm just kind of drawing maybe where, where atoms in this crystal lattice kind of align along the surface. Now we might have some cases, so there are 3 cases. So we said there are the atoms on the surface can oxidize. So let's just say this is the atoms just below this surface layer. And we have pieces of metal that form chunks of metal oxide. So this would be metal oxide. And we might have one case where the metal oxide, just due to the ratio of sizes of atoms, due to the size ratio of atoms, the metal oxide forms and there are gaps between the little bits of metal oxide and the metal underneath. So we might have one case where just due to, oxygen's size, oxygen's atomic mass, and the metal's atomic mass, and the way that they form, how tightly they bond to each other and what the size of that chunk of metal oxide that forms right along the surface is. There might be some case where there are gaps. There might be some case where it kind of forms this nice a very nice layer with good integrity. So maybe there are no gaps or very small gaps, or maybe these are even overlapping slightly, but there's enough so they all fit in. And in this case, we have the oxide layer protects. And the key thing is that there are no gaps. And these would be bits of metal oxide. And then you could imagine a case, all right, well, what happens if the metal oxide pieces are too big, right? Here we have too small, here we have Goldilocks, and here we have too big. Well, if they're too big, then they can't pack nicely onto the surface. They all sort of prevent each other from packing onto the surface, and basically what happens is little chunks come off. If the metal oxide unit cells are too big to pack nicely onto the surface. So in this case, oxide comes off, and then this exposes more metal underneath. So here, there are gaps because the metal oxide is too small compared to sort of the unit structure of the metal. Here it's just right. Here the oxide's too big. And in this case, you could get corrosion, and in this case, you get no corrosion. So what is this? Here we have minimal corrosion. And here we have corrosion, because the oxide can get in and attack through the gaps. And here we have corrosion, because once the oxide layer comes off, it exposes more metal. So I said, as engineers, right, this is a pretty qualitative description of what's going on. But as engineers, we oftentimes want to quantify these things. And when we go to quantify these things, we can do so via a quantitative description of the volumetric sort of unit cell size of an oxide compared to the volumetric, let's say, unit cell size of the pure metal. And we do so via the Pilling-Bedworth Ratio. The Pilling-Bedworth Ratio, oftentimes capital R sub PB. And basically what this is a description is the volume of a unit cell of oxide divided by the volume of a unit cell of the unoxidized metal. And it turns out we can actually, we can quantitatively predict these things via a description of the molecular weight of oxide times the density of the metal times this quantity n. This is a different n. This is an n that is sort of related to the n we talked about before, but I'll get to it in just a moment. And times the molecular weight of the metal times the density of the oxide. So let's sort of define all the terms in the of these things. MW is like the molar mass or molecular weight, or anything that we what's going on there. Rho is the mass density. So this would have units of kilograms per meter cubed or something like that. And N is the number of atoms of metal per one unit of oxide. So anytime I see a new equation like this, I like to think about units. So if we think, all right, what is, for example, the density of metal divided by the molecular weight of metal? Well, this would have units of kilograms per meter cubed, and the molecular weight would be something like, kilograms per mole, or grams per, mass per volume, and then this would be mass per moles. So basically just this part that I've highlighted in purple would have units of moles per meter cubed. And this would basically have something of, that's kind of like 1 over volume. So basically what I highlighted in purple here is basically analogous to what we have over here, this sort of 1 over volume of metal in the denominator there. Alternatively, if I highlight these other parts in green, then molecular weight would be mass per mole, and the density of the oxide would be mass per volume, and then this would basically be meters cubed per mole, which is basically a volume that a mole of the oxide stuff would occupy. So anyway, when you take the product of these two things, you end up with Pilling-Bedworth ratio, which should be dimensionless. Because N is also dimensionless here. So basically this is a ratio of volumes, that the volume of a mole of oxide would occupy versus a mole of just the metal. And it turns out that this Pilling-Bedworth ratio helps us predict these effects over here. So in this case, the Pilling-Bedworth ratio is less than 2. In this case, the Pilling-Bedworth ratio is about 2, maybe just a little more than 2 sometimes. And in this case, the Pilling-Bedworth ratio is greater than 2. So let's just put in a couple examples of actual Pilling-Bedworth ratios calculated from actual materials. If we have calcium, then this Pilling-Bedworth ratio is 0.64. And zinc, the Pilling-Bedworth ratio is 1.58. And we know that if we just drop a chunk of metallic calcium in water, that corrodes very, very quickly. Like, it dissolves practically. And if we put in a chunk of zinc, it lasts for a while, but it doesn't last forever. And in fact, people are using zinc to make slowly resorbable stents for, like, propping open arteries and such. Pilling-Bedworth ratio is about 2. One of the best examples of this is chromium. So pure metallic, just chromium by itself would have a Pilling-Bedworth ratio of 2.07. And, chromium is magnificently resistant to corrosion. And then a couple materials with high Pilling-Bedworth ratios. So you know how certain metals can have different have different oxidation numbers. Well, for example, iron 3 oxide has a Pilling-Bedworth ratio of 2.14. Vanadium has a Pilling-Bedworth ratio of 3.25. Vanadium actually could have a couple of different valence numbers, and in this case it would be vanadium 5 oxide. So anyway, these materials, right, like iron rusts and it rusts and it rusts and it rusts, and eventually it all goes away. And that's a consequence of having its Pilling-Bedworth ratio that is a significant degree higher than 2. All right, so let's think about some of these Pilling-Bedworth ratios in the context of actual uses of biomaterials, and in particular metallic biomaterials. So before people used ceramic polymer composites for dental fillings, ceramic polymer composites for dental fillings, people used gold, which was great for fillings but very expensive. And people also used silver mercury alloys. And the reason people used these two materials for dental fillings was because mercury and silver and also gold have these high potentials. So they basically don't oxidize. This reaction is unfavorable for them. Alternatively, we could think about different strategies for protecting against corrosion. So we might think about stainless steel. And the key thing that differentiates stainless steel from just, normal steel is that it's made from iron and chromium. And the key thing with stainless steel is you can have potentially up to like 20% by mass. So you could have stainless steel that's mostly iron, sometimes a little bit of carbon and maybe some other junk. But the key thing is you could have up to 20% chromium by mass. And what the chromium does is takes iron's very high, or high-ish Pilling-Bedworth ratio and bring it down to something that's closer to what native chromium would be. So by alloying iron with chromium, you can tune the Pilling-Bedworth ratio of the atoms on the surface. So that's two different engineering decisions that people make in the context of biomaterials to avoid corrosion. One that's just choosing the proper metal with the properties that you want. And then the other is an engineering decision to combine metals to take advantage of the other strategy, which is forming a protective oxide layer. Thanks for your attention, and I'll see you later.